One of the things that we'd like to be able to do with radicals is to solve equations that involve power functions. For odd powers, that's very easy because the power functions are one-to-one and the radical functions are actually their inverse. If we have an odd power of some expression equal to any real number c, and an odd integer power p, then for any expression, x to the p equals the number c is an equivalent equation to x equals the pth root of c, meaning they have exactly the same solutions. So that means that we can use the pth root to get rid of a pth power, as long as p is odd, right? And this is a specific case of a very general move that we'll use over and over again. If our variable is inside a function, we can rewrite using the inverse. So if we have an odd power appearing in an equation as the only power of x, we can isolate that odd power, rewrite it using the odd root property, and then continue solving to get the variable by itself. So that's going to look something like this. Our first example, we have x to the third equals 25. And notice x to the third is already by itself. So 1 is finished. Right? X to the third is already isolated. We'll rewrite this using the odd root property. So x equals the third root of 125. And then x is already by itself, so all we have to do is calculate the third root of 125. We can use a calculator for this if we'd like. We get x equals 5. Just to check, 5 to the third really does equal 125. So that was the most basic kind of equation that we can solve using this process. In this next example, our power expression is already isolated, but after we apply the fifth root, so 2x plus 1 is equal to the fifth root of 32. In other words, 2x plus 1 is equal to 2. So we've applied the fifth root, but x is not by itself yet, so we need to continue working to solve for x. We'll subtract 1 from both sides and divide both sides by 2, and we get x equals a half. To check that that really worked, again, we'll plug in. So 2 times a half plus 1 to the fifth power, well, that's 2 to the fifth power, which is 32. One more example. In this example, we notice that our power expression is not isolated, right? It's not the only thing on one side of the equation. So the first thing we need to do is get x minus 3 to the 7th power by itself. So we need to get rid of this 8. We'll subtract 8 on both sides. And then we need to get rid of this 4. We'll divide by 4 on both sides. So now we have isolated our power expression. Now we want to apply the odd root property, rewriting x minus 3 to the 7th equals negative 1 as x minus 3 equals the 7th root of negative 1. Now the 7th root of negative 1 is just negative 1, because negative 1 to the 7th power is negative 1. So now we have x minus 3 is negative 1. We'll add 3 to both sides, and we get x equals 2. To check that, we'll plug in 4 times 2 minus 3 to the 7th power plus 8, taking that whole thing and throwing it all into the calculator, we get that that really does equal 4. So we can use this odd root property when we have a variable expression taken to a power, and that's the only occurrence of the variable. Right? When we have multiple occurrences of the variable, we need to do our more complicated techniques that we use for polynomials. Now, some of these equations we can pretty easily solve as polynomial equations as well. For example, if we have x to the third equals 125, and we think of that as a polynomial equation, well, we want to get 0 on one side, so we'll subtract 125 on both sides. But I know that 125 is a perfect cube. So this is a difference of cubes. I can factor. So x minus 5 times x squared plus 5 times x plus 5 squared is 25. That works out to 0. So x minus 5 is 0, or x squared plus 5x plus 25 is 0. Remember, this is prime. And so far we've said, yeah, if that happens, that's just never 0. We'll see a stronger reason for thinking that that's never going to be 0 in just a little while now. But here we add 5 to both sides and get x equals 5. That's the same solution we got with the odd root property, but I think that the odd root property gives it to us a lot more easily. So if we have an equation that we can solve as both a polynomial equation and a power equation, we get the same solution either way, which is good.